Hello, everyone, and welcome to course P15. It's from the GMAW Issues and Resolutions series. My name is Bob Bosworth. I'm going to be your host for a little while here. And during this session, we're going to explore the elements of an efficient GMAW process. So let's get started here. I'd like to begin with talking about the essentials. The essentials are gas flow. We'll talk about gas flows, and there's many courses that run into gas flow. To make sure that the gas is there, the presence, there's actually 7 purposes for it, and they'll be touched on in this particular course. Of course, we have a contact tip, different types of contact tips, and we'll talk more about the temperatures and the melting points of these later on. In more advanced series, we actually start talking about this gap, this space in here, the surface condition, the space that there is in it, and so forth. Consumable tungsten, or excuse me, consumable wire feed process, where this is what makes it a semi-automatic process when you're welding by hand, because you have an automatic feed. Now, the real key element here is this little yellow bundle here that we spend our lives staring at, trying to figure out what it is, and it's known as plasma. Now, plasma is the reason we can get the penetration that we do. Plasma is very, very hot. And the problem with plasma when it comes to consumables and so forth is plasma gets much hotter than, of course, the melting point of our filler metals, which are usually, if they're steel, about 2,900 Fahrenheit. But this piece of copper here, and even the edges of this nozzle, they're all going to melt at somewhere around 1,800 degrees Fahrenheit. So it makes it very easy for these consumables to be destroyed by the heat alone that's coming off, and just with the emanation being in the zone. We'll talk about this area right in here later on where it comes to extension, how far the wire sticks out before it gets pinched off. This also has a lot to do with the life of a contact tip. So let's bump into temperatures here for a minute. So our contact tip melts, as we said, about 1984, a little higher than I said. You can get various types. You can get some that are class 2. Everybody's heard of zirconium. A couple of companies have contact tips that have enriched inserts in them that utilize some tungsten. They seem to hold up very well, but they're not the greatest when it comes to conductivity. So, there's challenges. They can all be met. So the electrode itself is going to melt closer to 2795, which is steel's melting point, depending on exactly what alloy we're talking about. And your mild steel goes at about 2600. So this is where we get our penetration. And this is actually probably a perfect time to talk about lack of penetration when it comes to gas metal, and how the efficientness of your travel speed means so much. If you try to move too slowly with these processes, you can actually get a deposit that'll start laying on top of other deposits. Your responsibility, anybody with a gun in their hand or responsible for where the gun should be, is to make sure that this plasma is out in front of and making contact with the base metal, and the deposit of weld is falling into that. Let's go through the shielding gas. So it starts off with temperature control. When you look at your diffuser, and you start looking inside your diffuser, and you start looking at these, there was usually little holes in here, right, to let the gas out. Those little holes represent a very thin section of the diffuser that's a heat stop. It's making sure the heat doesn't get further up inside of your diffuser. If it gets up inside your diffuser, it'll start to melt the gasket behind the gasket that's holding the gas to make sure it doesn't go backwards. It'll do all kinds of damage. But in the end of the day, we want to make sure that we have the gas flowing consistently. Now, our air is no good. There's so many things wrong with our air, and the first one happens to be the 78% nitrogen we have in our air. Our breathing air is 78% nitrogen, 21% oxygen, and almost 1% argon, which happens to be our shielding gas. It actually comes from the air separation process. When they separate those 3 gases, companies like Linde and Air Liquide, they separate those gases, and they separate them, and they ended up with all this argon, which happens to be one of the inert gases that we need for welding. Protection of the base metal. If we're going to melt something, we need to protect it from the nitrogen. Nitrogen has a very specific metallurgical negative impact as well. Steel recovery, alloy recovery. When we add carbon dioxide, we start to make metallurgical changes to the weld. Sometimes toughening, sometimes it might make it too hard, depending on what that alloy is. It does change things a little bit, though. And one of the things that the higher the manganese, or sorry, the higher the argon content is, the more manganese depreciation we end up getting in the weld. Protection of the cooling of the weld metal. This is important to have trailing gas protection. If you push a gun way, way too hard, this is where you're going to get bit. Because if you push it too hard, that tail, especially when you're welding at speed, you get around 50, 60 inches a minute on a robotic application, you're going to have a problem having gas coverage in the back if you're pushing forward. So I always tell people, don't push, don't pull, go straight on, because that's going to give you your best control over contact tip to work distance. Go straight on and only push or pull if you need to. Remember, those push and pull is a parameter, not a choice. It's a parameter based on an event that you see, and you would make that choice. Another class for another time. We got to protect the weld deposit, of course, and last thing, we have to create these different types of plasma, which have an effect on the base metal, which have an effect on the type of plasma, which have an effect on the depth of penetration. There's all kinds of things that happen as a result of that one. That's why I kind of put it in red as being one of the most important. So the area right in here is one of the ones I like to focus on. There's an area right here that determines and is known as extension, electrode extension. The extension is the distance that the wire can come out of the contact tip, and make it before it's pinched off by the voltage. Now, I'd like everybody to take a moment and think about something for a second. Visualization is important. Voltage just tells us where this gets pinched off. If you turn your voltage up, it starts to make the extension shorter. If you turn your voltage down, it makes the extension longer. Now, this is one of the effects of trim. Trim, if you turn your trim down, the voltage the wire feed speed, of course, stays the same. That's the whole idea with pulse. But your extension will be allowed to go further because the voltage will be slightly lower. Hence, if your voltage or your trim is too high in pulse mode, you said you're going to be much shorter, drawing all this plasma in closer to the contact tip and melting the end of it. I'll show you some good examples of this later on. So thank you very much for this portion of the training. We look forward to talking to you again. Thank you very much. Bye-bye.